Hey, I'm on vacation every single day, cause I love my occupation. Hey, I'm on vacation. If you don't like your life, then you should go and change it.
Started? Yeah?
Alright, yeah.
We're good? Okay?
Yeah.
Alright, everybody, welcome to Zhengyi Luo's PhD defense talk. I'd like to thank the committee members from far away. We have Karen Liu from Stanford, we have Jason Peng from Simon Fraser and NVIDIA, and we have Shubham and Vanya and myself. Today's talk is a culmination of many years of work, and it's just great to see it all come together today. So, if anybody in the room or on Zoom has any clarification questions, maybe I could, you could feel free to ask them if they're very short clarification questions. Otherwise, we'll have a longer Q&A at the very end where you can ask some longer questions. Maybe I'll ask David, do you think you could keep an eye on the chat?
Yeah.
If somebody has like a short clarification question, otherwise we can save it for the end. Yeah. All right, and then the way it'll work is we'll give the talk, and at the very end, we'll go in order of, like reverse order of the committee members. So I'll ask Karen and Jason to ask some questions, and then followed by Shubham and Guanya, and then myself. And then we'll open it up to the room if anybody has any questions, and also on Zoom. And we'll do that for a couple of minutes, and then we'll formally end. We'll have just the committee members stay in the room and on Zoom, and Zen and other students will wait outside, and then we'll call you back in with the final result.
Final result.
Yep. All right, so that's just the procedure. So again, thank you everybody. So let's get started.
All right. Thank you everyone for coming, and the friends on Zoom as well. Today I'll present my PhD thesis, Learning Universal.
Did you record Zoom?
Yeah, it's recording.
Just want to double check here.
David, it's recording.
Yes, it is.
All right. Today I'll present my PhD thesis, Learning Universal Humanoid Control. This is with my thesis committee, Chris, Guanya, Shubham, Karen, and Jason. So I want to start by making a bold statement that the humanoid is one of the most promising physical embodiments for embodied intelligence. In simulation, humanoids can produce human-like motion for animation and graphics, and it can be served as a general-purpose platform for embodied AI. And in the real world, we have imagined them to join the workforce, make us a cup of tea, and go to places that humans don't want to go, and do things that we don't want to do. Now, the central question for this thesis is how do we scale up the humanoid control capabilities that are needed to make humanoids useful? And our answer is scaling up humanoid motion imitation. To put this question into perspective, we'll scale up humanoid control in 3 axes. The first axis is complexity. If we scale up on this axis, the input dimension will grow, and output degree of freedom also grows. We'll go from whole body control, adding hands, so whole body dexterity, and then visual whole body dexterity. As you can see, the degree of freedom of the output grows, and the input dimension going from just state to vision. The second axis we'll scale is task diversity. We do not only want to solve one single task, but also diverse tasks. And finally, the final axis is realism. We want to solve tasks first in simulation and then in the real world. So the 3 axes, and where do we want to go? We want to get to here. High complexity, very diverse tasks, and in the real world. This is how we solve robotics. And I will provide a 3-step recipe for scaling up humanoid control. Step 1, motion imitation. We'll first learn to move like humans. Step 2, forming a control prior for reinforcement learning such that we can explore like humans. And finally, learn to grasp objects like humans and manipulate objects like humans. I'll present a series of work starting from motion imitation for simulated and real humanoids, followed by forming a control prior for reinforcement learning, And finally, grasping diverse objects with both blind and visual agents. Will enable humanoids to move like humans, explore like humans, and then grasp objects like humans. In terms of related work, this thesis stands upon the shoulders of many giants. Many prior work has been proposed to work on these 3 steps separately. However, I would say most of them solves single tasks using small-scale curated data sets. And you can also see a progression from step 1 to 2 and to 3, since the complexity really grows. And we should solve these tasks from step 1 and then to move on to 3. And before I dive in, I'll very quickly go over the background for humanoid control. So we'll have a humanoid, have some kind of state of the humanoid, feed that into a policy. The policy will compute an action, feed that into the dynamics function or in simulation or the real world, and then we'll form a loop. And from simulation and real world, we'll get some reward to optimize our policy to get better. And the state we'll consider is proprioception plus the task observation. Proprioception would contains the joint position, rotation, velocities for the humanoid. And the task can really be anything. Whichever task you want to solve, that will be going to the task variables. The action would be PD target controllers for every single joint on the humanoid. And then finally, since simulation and real world are usually not differentiable, we'll use reinforcement learning to optimize our policies. And this is a visualization of what that would look like, reinforcement learning training. Every RL practitioner is very familiar with this type of jittery motion and flopping around. But this is not how we learn. Humans do not learn by flopping our limbs around and then get terminated because we hit some condition. We learn using human-like motion, which looks like this. So how do we enable our agent to learn like humans? And that brings us to step 1. First, we'll learn to move like humans. And we'll do this by scaling up motion imitation. The task of motion imitation is the task of translating kinematic motion to dynamics. Kinematic motion contains the joint angles of a human, and dynamics means the joint torques. Basically, the task is, if we give you a reference motion, we want to control our simulated humanoid to produce the exact same motion. It's a motion imitation or motion tracking task. The input for the motion imitation task would contain proprioception and the reference motion. The reward would be the 1 frame difference between the current simulated state and the reference motion. And the one thing that I care the most about for the motion imitation task is the so-called success rate. Can our agent or our policy imitate a full sequence of motion without deviating too much from it? For example, this is not a successful imitation. Well, this is. Now, this is a very challenging task because, as humans, we know we can do many amazing things. This is the largest academic data set, very popular in computer graphics and computer vision community, the largest human motion data set amassed. It has 10,000 diverse motion clips, ranging from just walking around to absolutely crazy ones like cartwheeling and backflipping. So we have this data set, and we want to control our humanoid to reproduce every single one of these actions. Now, the focus on motion imitation really, on success rate and motion imitation, really brings in a severe forgetting problem. This is what the typical success rate would look like during training. And after about 2 to 3 days, the success rate will kind of plateaus at 96-97%. And in terms of 10,000 motions, that's hundreds of motions you will never be able to learn. I call this phenomenon, the policy learns how to cartwheel, but then forget how to backflip. Your performance really plateaus. Here I will present a simple idea to solve this forgetting problem. We'll borrow ideas from continual learning and progressively allocating new network capacity to learn harder and harder motion sequence. What do I mean by that? Basically, if we have a full motion data set, 10,000 motion clips, we'll first train a policy to imitate all of them. The performance will plateau at some point, but we can evaluate our policy on the full motion data set and find the hard ones. And then we'll just train on the hard motion. And we can keep doing this and keep training new policies, initializing new network capacity to learn these harder and harder motion sequence until we run out of motion. In the end, we'll probably just have 5 motions, and then we will imitate them with one policy. I think the key insight here is that we can always overfit to a selected number of motions. And once we have obtained a sequence of policies, or we can call them primitives here, we can learn a composer to dynamically switch in between. And the key here is we'll keep the policy and primitives frozen such that we can preserve their capabilities. And very specifically, given the kinematic motion and a sequence of learned motion primitive or motion policy, we can learn an additional composer to dynamically switch in between. Relatively simple framework, and the key bit here is frozen primitive policies. And this is also the difference between this and a mixture of expert. Basically, in mixture of expert, we will be training the primitive policies together with a composer. But here, we're really freezing the primitives such that we don't have the forgetting problem. And with this pipeline, we achieved 100% motion imitation success rate. So we imitate every single one of motion from the amassed data set. We achieve 25 millimeter per joint position error, basically very low error. We also achieve smooth motion, so very low acceleration error as well. And with this, we are able to imitate very diverse and very challenging motion like this. And this obtained us the PhD, Perpetual Humanoid Controller. To recap, let's look at our 3 axes that we want to climb. We have obtained PHC, a whole body controller that can solve diverse tasks, imitating the full amassed data set. The good is that we have a very capable motion imitator, 100% success rate with one single policy. It can generalize to on-scene motion relatively well. You can use it to control your avatars using motions from post-estimation or text-to motion. It is robust and can recover from fallen states. However, PHC can only be applied to motion imitation. What do I mean by that? Basically, the moment you want to apply PHC to some other task like terrain traversal or grasping object, it will fail miserably. The reason is PHC is never trained to do any interaction. So if we want to handle these type of interactions, such as walking on diverse terrains and grasp objects, we have to train new policies from scratch. But we don't want to do that, do we? You will ask me, Zen, we already learned to move like a human. We already have this amazing policy that can do all these diverse motions. We don't want to train policy from scratch. We have learned the motor skills to produce almost all human motion. Well, from a large data set, not all, but a lot of different human motion. So we don't want to train from scratch for all these new tasks anymore. And then that brings us to step 2. Learning control prior for reinforcement learning such that we can explore like humans. So the issue here is that humans do not learn from scratch for every single interaction task, every new task you throw at it. We are born with a set of pre-programmed control priors. We do not learn from scratch. We do not learn by flopping around and then get terminated when we hit some termination condition. We, starting from babies, can do some basic things like grasping object and move it around. We have very strong priors. So how do we enable our agents to explore like humans? Well, we can preload our agents with presets of motor skills as well. So consider the space of all possible human joints. What we want to do is we want to find a space or prior space that contains human-like motor skills. And we want to sample from here. Throughout this talk, really apologies for the imprecise terms. I will refer to latent space, control prior, motion representation, motor primitives. They all mean kind of the same thing. It's a little hand-wavy. For example, motor primitive is a very overloaded terms in simulated control. And in this space, I kind of refer to them as very similar things. It's a latent space, control prior. This is not a new idea. There are many prior work, many great work on this space forming a control prior. However, the main issue that I have identified is that all of these work use small-scale curated dataset for certain purposes, like locomotion or training a gaming character. What that leads to, when you train with small-scale dataset and not try to scale it, is you will find a narrow latent space that contains the actions you wanted, but it will not support other tasks. And what I want to achieve with this work is obtain some kind of universal control prior that we strive to solve all tasks. You'll actually see me learn control prior to almost every task that I will do in the following talk. So to kind of conceptualize what are we looking for in a good control prior? We have three main axes. The first one is random sampling. So random sampling from this control prior should lead to human-like motion. Pretty self-intuitive. Our control prior should lead us to explore like humans. The second is it should be universal. It should cover all of the motor skills needed to perform a large motion data set. And if we have this type of universal capability, we hypothetically can apply it to many different tasks. And finally, it should speed up downstream tasks. Very self-explanatory. And I really do want to emphasize on the universal part. This is essential. We don't want our control prior to be crippling. It should not constrain our policy such that it can only solve a narrow set of tasks. We want to apply it to all kinds of different tasks. So how do we do this? Now, consider the motion imitator, PhD. What does it do? Give an imitation goal and proprioception. It will compute the action needed to imitate this sequence. And that sequence is human-like. So PhD can produce actions that are human-like. So what we want here is we want to form a distribution of proprioception conditioned on the action such that if we sample from this control prior, it will lead to human-like motion of the humanoid. So this is exactly what we'll do. We'll use the motion imitation task because motion imitation leads to human-like motion. We'll have imitation goal and proprioception. Feed that into a encoder-decoder structure. This basically is a VAE. And basically learn a VAE with the motion imitation task. We'll learn an additional prior, but this is just more bells and whistles to make the VAE structure a little bit more fancy. To put it very concretely, the encoder will compute a latent code, and decoder, using that latent code, will compute the action. And the main difference between a usual VAE and what we have here is the learn prior. So instead of learning a zero-mean Gaussian, we will learn using a learn prior, the more diverse Gaussian distribution, as you may say. And then, yeah, just learn this policy. Any questions? Unclear part? All right. So to learn this VAE structure, we'll use the motion imitation task and PhD as the teacher. So my first instinct with this structure is, okay, we can just use motion imitation and reinforcement learning to train this. Trust me, I have tried. The problem here is if you want to train a VAE, you have to sample from the latent space. And to train reinforcement learning, you have to sample from the action. And this makes the training problem really, really hard. the gradient becomes way too noisy. So instead, we'll resort to supervised learning and use our great pre-trained PHC policy to compute pseudo ground truth actions and just do online distillation. It's the same task, same pipeline. We just at runtime we'll query the expert policy or teacher policy and do distillation. And then supervised learning will take care of everything else. And after learning, we'll call this pulse, physics-based universal humanoid motion representation. So how do we evaluate it? Remember the 3 axes: random sampling, universal, speeding up downstream task. And I will very carefully make sure that we hit all 3. The first one is random sampling. To random sample from this space is relatively simple. We just have the decoder, the prior, and we'll inject Gaussian noise to the system. And if you look at this structure, you'll see this is exactly what we wanted before. We want the action distribution conditioned on the proprioception. This is the result of random sampling from this latent space. You can see, even though the only input to the system right now is Gaussian noise, the humanoid is doing human-like things. They're standing upright. They're doing things that I cannot explain, but they're doing things. They're not flopping around anymore. And when I was developing Pulse, when I saw this, I knew I've struck gold. This is really great because now if we use this latent space as the training space, training action space, we'll have human-like motion as for exploration. Now, downstream task. How do we learn this? If we have some other task, we have some task input, we'll just do hierarchical RL and train additional policy and use our pre-trained prior and latent space as new action space. So hierarchical RL, train a new policy, and use reinforcement learning on top of this pre-trained control prior. And this is the training visualization. Before, we have this random flopping around and hitting the ground all the time, to this new visualization where we use our control latent space for training. You can see the humanoid already has its basic motor functions. It's walking around and it's doing things. And if we want to train different tasks like reaching speed, it doesn't take that long when you sample some running-like motion and you start running and you get a reward and then you started learning. Your curve will grow really fast. So to solve diverse tasks, we'll consider 4 generative tasks. First one is reaching targets, followed by reaching different speed, striking object, and walking on terrain. I want everyone to pay attention to the last 2 tasks. These 2 are humanoid object interaction tasks. PHC has never been trained on interaction tasks, and I have mentioned before, PHC cannot be applied to these tasks directly because it has been never trained for those. However, the motor skills we distilled and learned from PHC can be used to solve these tasks. Is it because the motor skills, for example for jumping, can be reused to tackle these tasks. The third one is universal latent space. Can our latent space or control prior cover all of the skills needed to perform a large-scale motion data set, such that we know we have good coverage? So we'll consider the motion imitation task. This is a good task to test whether you have good coverage in your action space. With a twist, though, we're not going to just do motion imitation again because that becomes circular, right? In this case, we'll consider the sparse motion tracking task. We'll make the task a little bit harder to make it more exciting. So instead of feeding the full body motion imitation goal, we'll do just 3 points, 2 hand and your head. And what that would enable us is to control our simulated avatar with just a VR controller and VR signal input. So headset and 2 controllers, 3 point, and we can recover the user's full body pulse. So not only we'll test the coverage of our latent space, we'll also get some policy out that's useful. Here is the results as well as comparison with prior work. So our motion representation is able to solve the task very well. Has pretty good coverage. It is almost as good as training from scratch. As we know, PhD is basically training a motion imitator from scratch. And our control prior, distilled from PhD, can be used to solve a very similar task. Now, this is a very challenging task because this is free-form tracking. This is free-form. The human operator can really be doing anything. So if your latent space or motion representation can only do certain things, you will not be able to solve this task. Your humanoid controller needs to react to many different actions and many different motion. And if your motion representation is crippling, you won't be able to solve this task. And we can see our controller scales relatively well and outperform all the prior work, which doesn't really scale up to have this type of coverage of a large-scale motion data set. So to recap, we do not scale up on our axis, but we have obtained a very powerful tool to move forward. We have pulse, and from PhD's motor skills, we can learn a motion representation that has universal motor skill coverage. It speeds up downstream task training a lot. It has generative capabilities akin to a foundation model where you can inject noise to the system and then you get something human-like out of it. Just like with GPT models, GPT-3, you can inject some noise and it spews out some other human-like text. The issue here is the policy, the latent space is not interpretable, and we'll need a two-stage pipeline to learn. First, we'll have to train PHC and then distill that into a representation. And there's no dexterity yet. Which brings us to grasping objects like humans. Dexterity and perceptive policy learning. And the first thing we'll tackle is grasping diverse objects with humanoid. So the task we will consider is, given an object and desired object trajectory, we want to control a simulated humanoid to grasp the object and follow the desired trajectory. So input is a 3D object and desired trajectory, and we want to get our humanoid to grasp it and then follow the trajectory faithfully. Now this is very challenging because objects are passive. Your actions does not always directly change its state, and you can very easily knock the object over. So it's a very hard learning problem. There's also very limited data. There will be no data that contains this type of in-the-air calligraphy with the humanoid tracing out omnigraph word. Nobody will think of to mocap this. So we don't have a lot of ground truth reference motion to train an imitation policy for this. And that actually leads to many prior work that just use the disembodied hand for grasping, because just motion capturing the hand and an object is slightly easier. Also, prior work usually just consider simpler trajectories, not as diverse as we're solving here. So the solution here, as I have mentioned, is step 1 and 2. What we'll do first is acquire a motor skill control prior such that we can solve this task easier. So we'll go to PHCX, a motion imitator that has fingers. We just add more joints to the humanoid and do motion imitation. Relatively simple. And then we'll distill that into a control prior, pulse X, similar things. And equipped it with these type of preloaded control motor skills, we will be able to design a training pipeline for the grasping task. The input would be object state, so this is the 6-degree freedom position and rotation of the object. Object latent code, this is the shape of the object. We'll use basis point set to encode the shape of the object. And then future trajectory, that are desired for the object. Combined with proprioception for the humanoid, And then you'll see this very familiar pipeline. We have the PulseX decoder and prior. Learn another policy, hierarchical RL, to train to grasp. And then this is the reinforcement learning loop again. Now, I will plant the seed here. Pay attention here. We're using ground truth object state from simulation. This is some would call magic perception, because you know where the object is at every single frame. The reward is very simple. Just two stages. First, approach the object with a grasping pose, and second is follow object trajectory. Now, this reward doesn't have any style or reference motion included. It just approach the object and follow object trajectory. And we can do this because we already have a pretty good human-like control prior, and we're only exploring with human-like motion. So we can just train this policy with very simple reward. And as I've mentioned, we don't have reference trajectory, paired full body motion, and object trajectories. So we just sample random object trajectory to train. Just sample randomly, it just moves, and we have the capability to do this. Why can't our humanoids? After this policy is trained, we can grasp diverse objects, follow diverse trajectories, using this type of human-like motion with the very simple reward that I mentioned. We can follow pretty challenging trajectories. So what would happen if we don't use PulseX? This is what happens. You can see the humanoid will use some very wacky style to solve this task. It's the same reward, same pipeline, but you can see the strategy the humanoid use is no longer human-like, and I would call it suboptimal because, while it can grasp the object, the humanoid does not remain stable, and the motion just looks quite terrible and somewhat scary. Now, with the control prior, we will be able to get out of this local minimum because we have this human-like movement baked in already.
Is the plus symbol? How do you compare the motion prior with the RL? Is a concatenation or just addition?
It's addition.
Okay.
Yeah. Basically, you have the prior.
Just A plus B.
Yeah, A plus B. Yeah, linearly. So it's like adding noise, and then you perturb the Gaussian with more noise.
I see. I see.
So to recap, now we took one more step on our axis and obtained only grasp, a visual whole body dexterity policy. It can generalize to unseen objects, grasp diverse objects, generalizing somewhat to unknown objects. However, it depends on knowing where the object is at all times. It also cannot, we cannot really tell the policy which hand to use. It will just use whatever hand it feels like. And also, you probably didn't notice, but the policy cannot put object down. Because if you remember, the state we fed into the policy doesn't really have any information for when to grasp the object and when to put it down. If we want to support it, we'll need to add more states. And there's no vision yet. The policy is blind. So next step, we'll give the policy eyes. So far, all of the humanoid control policies, everything that I have presented, are blind policies. The humanoid has no perception. Sometimes it has magic states from simulation, but that's not really what humans see, right? We have perception, we have vision. So given a humanoid that are equipped with only proprioception and vision, and you will have touch, you will have contact sensors, but that is part of the proprioception. So proprioception plus vision. How do we learn local manipulation tasks? How do we get it to pick and place, open drawers, etc.? The issue here, once we move to a more vision-centric policy, is vision requires active perception. Vision-based policy no longer knows where the object is, so the first thing we'll need to do is search for the object. This is the same setting as only grasp like before. The first frame, when you initialize the humanoid, it's no longer looking at object. So if you only have proprioception and vision, you don't know where the object is. And what we wanted to do is to kind of look around, search for the object. Okay, I need to look down and then find the object and then start grasping it. The second is, how do we specify task goals? So consider a kitchen cleaning task where the humanoids need to find specific objects in cluttered scenes. We have 10 objects. How do we tell the humanoid which one to pick up first? So the input for this task would need precise 3D location of desired object, when to pick it up, when to put it down, and where to put it down, right? So we need all these type of information for the policy to control it. Now this is not really scalable because what about we want to open drawers? Do we add when to open drawers, where the drawer is, when to close it, how much we want to open it? Do we feed it more states? We already have vision as input. And vision, I think, is a very general purpose interface. We do not use all these state variables to solve many tasks. A lot of the tasks we just use our vision to solve it. So since we're moving to vision, a kind of a general purpose interface already, I no longer want to add all these states to support new tasks. And another drawback for this type of, we'll just add more state, is to support new tasks, now you have to retrain your policy, which is not really an optimal thing to do. So instead of using state variables, we propose a relatively intuitive way of specifying the task goals, which we call perception as interface. So imagine you're playing a video game. What do we usually first see? It's some kind of instruction in the screen, right? So it will give you some text, says, okay, this is the video game, this is what you're seeing, this is what you should do, and then there's a lot of visual markers that pops up that tells us how to play the game. This is very similar. Instead of giving state variables to our policy now, we'll just paint everything on the visual spectrum for the humanoid. So instead of giving state variables, we'll say, okay, if you look at your input vision, your input image, if you see some squares, white means don't use this hand. Purple means use this hand, but don't touch the object yet. And blue means, okay, use this hand and you should be touching the object right now. So basically this tells you when to pick up object. And the object of interest will be masked as green. This is an interface that can be applied to real world as well. We can just do semantic segmentation and mask the object and say, okay, this is the object of interest, pick that up. And in terms of where to put object, we'll just draw the goal position, the rough goal position for the humanoid to grasp the object and put it to that place. This is what the framework will look in action. Basically, you can see the squares changing color when it asks the humanoid, okay, I'll change it to blue, now it's time to grasp. And the object, for example, is not green, but for the vision for the humanoid, we'll paint it green such that we tell it this is the object of interest. And to train this policy, sorry, I haven't figured out a better way. So we'll just do brute force visual RL. Stack up more GPUs. The reward is very similar to OpenGrasp. It has a pre-grasp reward, adding a look at object reward, and then target position reaching for the object. The only thing added is we're encouraging the humanoid to look at the object. And we'll train this end-to-end, suffer from a 10 times slowdown, because if we're looking at the state, the proprioception and then is about 900 for the humanoid. But now we add vision. It's going to be 128 by 128 times 3. Now that's a orders of magnitude increase in input space. So, and plus rendering makes things slow. So this task is really, really slow to train. The architecture we'll use is pretty straightforward. We have the proprioception and perception as input. Perception will be processed with a very simple 4-layer CNN. You will laugh at it if you do computer vision. But this is what we have to work with high-speed simulation and massive amount of data throughput. We'll follow that by MLP and a GRU to add some memory. Our familiar friend, motion prior. This is the pulse, this is latent space, similar to OmniGrasp. And we'll train this architecture. And if we compare these two, the only difference is basically the input. We're replacing the object state with perception. So just perception, nothing else. I was quite surprised that this actually worked. We're able to grasp diverse objects with purely vision, this purely perception as interface. It can now actually put down the objects as prompted, and also specify which hand to use. And you can see it uses different strategies to grasp different objects with different shapes. And for tables, it uses two hands, one hand with the basket, monitors. Yeah, so able to grasp objects with purely vision. We also apply it to a more challenging kitchen scene. In this video, I want to demonstrate some kind of emergent memory, which I will point out to. So right there is when the object actually goes out of view. But since we have some kind of memory, it is able to reach for the object, actually grasp it, and then follow the blue marker here. So we'll see that again. So there, see the object, go out of view, but still successfully grasping it. There's also emergent search behavior. As I've mentioned, we will paint the object green. What if the object, in the beginning, there's no green object? The policy actually learned to, okay, there's no green object, I'm going to turn around and search for it. So if it doesn't search, if there's no object, you're going to keep turning around and trying to look for it. But you can kind of see it here in the very beginning. So no object, I don't want purple. Oh, find the green and grasp and start following trajectories. Turn around and find the object. So to recap, now we scale up one more step and have visual whole body dexterity. The good is now we can grasp diverse objects with perceptive simulated humanoids, but not 100% success rate. It's very expensive to train. Takes at least a week, unfortunately. And I feel like this is just the starting point.
Why the PDC video is a little bit jittery? So sorry, is that from PhD and Pulse or from Vision? Because you didn't show the first person view of PhD and Pulse, right?
It's from Vision.
Got it.
So we don't have any stabilization. And if we look, so there's two flows. First, we have built-in stabilization. There is a shaky cam. If we mount a camera and we move, it's actually very shaky because if we don't have image stabilization, the image will be very shaky. Our head actually is not that stable. The second is we just don't have any prior to say just stay still. And Chris has a very interesting hypothesis for this. Is doing high frequency movement for structure from motion. Not sure if that's true, but that's one of our explanation.
Cool, got it.
So how about real humanoids? Real humanoids promised. Real humanoids will be delivered. But we're back to square one, back to step one, learning to move like humans. We'll consider two humanoid, the full-size Unitree H1 and Unitree G1, which is more child-sized but more agile. The issue here is we want to transfer our motion imitator, PHC, to the real humanoid. This is very challenging because human motion is not compatible with the humanoid. There are many quantities that are not measurable in the real world. Sim to real gap is pretty huge, and a slew of different problems once you move to real humanoids and real hardware. The solution here first is we'll do motion retargeting. How we do this is we'll first find the human body that best match the humanoid, do a shape fitting, and then we'll do inverse kinematics to fit the body shapes, the body key points of the humanoid, and then retarget human motion to the humanoid. The reason why we do this is, as you can see here, with the feet of the humanoid, it is very wide. If you just directly do retargeting, you have humanoid walking like this instead of walking like this. So we will first fit the shape and then do retargeting. And after this process, we will be able to get a large-scale data set to do humanoid motion. And then the training procedure largely stays the same as PhD, plus sim-to-real transfer. Sim-to-real is a lot of randomizing friction, mass, control delay, adding perturbation, pushing the robot, and tuning the coefficient, reward coefficient for every single one of these turns through graduate student descent, or in my case, Tyrant descent. Tyrant is my close collaborator on all of my real humanoid experiments.
Ascent.
Yeah, ascent, since we're doing reward climbing. But basically, tuning all of the reward coefficients. And I've seen Tyrant did change one single parameters, and the humanoid suddenly starts walking. So this is really more an art than a science at this moment. And I think we should really quantify how do we tune reward for sim-to-real transfer. And adding weeks of tuning, updating state designs to accommodate input, fix the robot, sleepless nights, cry a little bit, break a couple robots, hopefully not breaking your back when you're trying to push get the robot up. Then you will get this type of policy, which we call H2O and only H2O. This is a teleoperation policy where you can control the humanoid to do different things with a teleoperator. So this is not autonomous. And we can do interesting things with a PhD-like tracker. Okay, let's not look at it grasping that knife. It's scary. The issue here is the humanoid is not that agile. It moves like a grandpa, walks like a grandpa, and moves like a grandpa, very slowly. Not that agile, not fluid motion. This is one-time speed, and it's pretty slow. And this is caused by the policy being way too conservative doing sim-to-real randomization. So because we added all those terms trying to bridge the gap between simulation and real world, we make the policy really conservative. And I'll very quickly go over a solution we're trying to cook up. In the interest of time, it's going to be very high level. So we try to align real world dynamics with simulation. The first stage is similar to before. We will train a good enough policy for sim-to-real and collect real world rollouts. It's going to be not so good. But with the real world rollouts, and we also have simulation rollouts, they're going to be different. And there's going to be some kind of difference between real world rollout and simulation rollouts. And with that, we can obtain signals to align the dynamics of the real world and simulation. We can learn a dynamics aligning function or policy to align these two dynamics. And once we learn that aligning function, we can fine-tune our policy in simulation again with this function, and then obtain a more real-world compatible policy. So sim to real, real to sim, sim to real. Sim to real sandwich. And with this, we obtain ASAP, a very agile policy to do many, many different tasks, and your favorite sports action. Now, for this policy, this is not one policy to imitate all of them. This is one policy for each motion. So we haven't really scaled this up yet. So to recap, with real humanoids, we have made decent amount of progress. On our realism axis, we have developed only H2O and ASAP. The good is we can transfer a lot of the learnings from simulation to the real world. sim-to-real transfer. We can map human motion, humanoid motion with ease. And I think aligning real world and simulation dynamics is going to be very key. But as you can see, the humanoid is not cartwheeling yet, so we're not PhD's full capabilities. So to conclude, we have gotten really far. We've climbed really high on the complexity and simulation, and we're just starting to climb the real world capabilities. There are a number of work that we have enabled humanoids to do, mostly in simulation, that I wasn't able to present. We got the humanoid to do pose estimation, to walk around, pose estimation with first person views, play basketball, text to motion, another text to motion. And here's the full references if you're interested. There are papers on my website. We covered these 7 papers in this talk. And just to conclude things, a little bit wrap up. In motion imitation, I think kinematic motion tracking is very, very important. I think this should be the first task every humanoid should be able to learn first. Second is hierarchical RL, and hierarchical learning makes things much easier. We need better priors for robotics. And just like all the language models or the vision language models have a very good base model, we, for robotics, also need that. And we have just scratched the surface of vision in the loop control. We need to speed it up. How do we train reinforcement learning with vision in loop? How do we add more tasks? And how do we train more efficiently with better architecture? All these, we're just getting started. Some high-level conclusions. I think figuring out tasks in simulation first and applying them to real world is very important. Stuff like grasping, reasoning, I think we can already do in simulation. And something that I really believe in is use what you have built and build what you want to use. You see, I reuse Pulse a lot of times in like 4 or 5 of my work, is because I really believe in it. I build it such that I can use it. We have climbed really high, but how do we actually get to there? You can see we're not there yet. So I will hypothesize another 3 steps. First, we need to learn behavior foundation models with vision in the loop. Verify that in simulation. Step 2, we should associate the behavior control prior with intent and language. And hopefully, I really believe in this, do real-world learning and scaling such that with this prior, we'll explore with human-like motion and be able to collect samples in real world and then learn efficiently. And that concludes my talk. I want to thank my wonderful advisor, Chris, whose unwavering support has been tremendously helpful. He gave me the chance to do a PhD at his lab, and he really is the best advisor ever. And I want to thank all my committee members, Guanya, Shubham, Karen, and Jason. Your work has been pioneering and inspiring, and then it really has been an honor to have you on my committee. I want to acknowledge all my collaborators who help me to get here. I want to thank my academic big brother Ye, who taught me everything I know, put me under his wings and taught me the ways of research. Jinkun and Yuda, who are my go-to guys for all the new techniques and all the academic gossip as well. Tairan, who introduced me to the bittersweet world of robotics, took me by storm, and the rest is history. I want to thank my mentors during internship, Sanya and Jason, Wei Peng at Meta, and Jim and Yuka, my mentors at NVIDIA now. Thank you all very much, and I love you guys. I want to acknowledge KLab. Thank you, Chris, and every member of KLab who has created such a warming community to do research. We talk, we chat, we collaborate, we have fun, we get through each other through our darkest hours. And obviously, my family, mom and dad, who are with us online today. Thank you for putting up with me with all these years. 10 years in the US to study abroad is no easy task. And you can see I look kind of young in all of these photos because they're all from 2019 when I graduated college, and that's how long I have not seen my parents, and I look forward to them for visiting us for graduation. I also want to thank my partner Georgia, who put up with me for working 60 and 70 hours a week. And my cat Nami, who actually physically wants to stop me from working too much. See, I cannot work anymore, she's on my computer. And all the friends who support along the way really helped me get through tough times, and I love all of you. Thank you very much. And just at the very end, I want to reflect where I started. This is 2019, an Apple internship where it got me into the physics-based humanoid control. This is following Jason's deep mimic and multiple control policy. We got a humanoid to walk, run, jump, and control it with directions. And this is a one hot vector to switch from different tasks. And going from there, I have become a certified gantry pusher, able to push gantry for all directions, following all kinds of different tasks. #1 humanoid controller tester in lots of my papers, controlling simulated real humanoids. And if you're in the Chinese WeChat social media, you'll see a lot of memes that I have made, and I call this the absolute win. Thank you very much, and I think I'm ready to take questions. Can wait for it to ask and guess what it's doing.
It's all right. All right, then. Thank you very much for
Perfect timing.
the talk. Yep. So we will go through the committee members first. I think we're gonna start with we'll go backwards order with Karen, and then we'll go to Jason, and then we'll go through the committee and open up to the room. So, Karen, if you're online, you could test out your audio, and then if you give us some feedback on the talk and any questions you have, that'd be great.
Okay, can you hear me?
Yes.
Yes.
All right, well, thank you for the wonderful talk and the wonderful work.
Yes, you can pull up.
I really like how you put it at the end, you know, build what you use and use what you build. This is a very, insightful wisdom that I like to impart to all my lab members as well. And then just the body of the work is amazing, and the way you presented it in such a clear and logical way that I really appreciate that.
Thank you.
So a few questions. I guess I'm just going to start from because you cover so much ground. I feel very hard to ask questions at every single part of your talk. So I'm just going to pick maybe a couple, and maybe other committee members can cover other ground. Okay, so start from the back. Robotics, going from human characters to humanoids. I want maybe the biggest part. You have done some work through collaboration on the humanoid side with your colleagues in CMU, and from what I gather, you said that the Synterreal is super hard. There's no systematic way of doing that. Maybe you should work with Kairan, and that seems like the solution to a lot of things. Why do you think it's the case? And I want to kind of narrow down that question a little bit, because I have one hypothesis, and I want to hear what you think about it. I think that the entire body of work that you presented on the computer graphics side heavily depends on this belief that ICGen is a good representation of the real world dynamics. I don't know if it's ICGen. I mean, I'm guessing it is. And then you can also see for some of the demos you show, they're not so realistic, right? Even though, especially when you're talking about when you're looking at dexterous manipulation part, It's just weird that you can actually pick things up that way. And this kind of this reliance, almost blindly reliance on Isaac Jim worries me a lot, especially if your end goal is going to the real world. And I think when you go from character animation to humanoids, you can do so much hacking, just like you said, right? Like sleepless nights, crying, all that, to get it to work, which masks all those potential issues that you generated, or one possibility is just this faith in Isaac Jim. So how do you think we could kind of rewind what you did, this journey that you took, like assumptions you made along the way, such that sim to real is not that hard?
Thank you for the great question. So the question, to rephrase a little bit, is sim to real and the assumptions that I've made on relying on a somewhat realistic simulator like Isaac Jim. I think, first of all, as hardware getting better and better, we're seeing a progression from training Isaac barely work with a lot of different randomization with better hardware, like going from Unity to H1 to G1. The sim to real gap actually gets smaller because the robot manufacturers are making strides to match the humanoid dynamics and simulation dynamics. So that's a good sign, but that's not an excuse to super rely on Isaac Jim. I think the real answer here is we should use simulation as to learn these type of priors, and then really not focusing on sim to real to solve everything. What the path we have taken for now is we're trying to do simulation for everything. We want to do all the locomotion and manipulation and transfer all of that to real. We just train from simulation and transfer that to real. And I don't think that will be the path. There will be some part of that we can learn very good control priors, or all of the so-called intuition, physical grounding that we can obtain from physics simulation. And as I have mentioned, I think moving forward, we really should start doing more simulation in the real world type of work, which I believe should help us with this over-reliance on simulation. So we should do it this way. We'll do simulation in learning, get all the kind of language grounding, try to get our language to understand the movement, try to ground our policies, such that you can form and maybe learn some grasping policies. It will reach and then try to grasp. And when we deploy it, some of them will be successful, some of them won't. But if we preload our controller with this type of motor skills, we can really enable real-world learning. And if we look at all the foundation model for robotics these days, they will do teleoperation. And I think with simulation, we can alleviate some of the data scaling for teleoperation by a lot if we can preload our controllers with this type of priors. And then we can use a little bit more real-world data to let it adapt to the real-world dynamics. So I think my answer would be, moving forward, we really shouldn't overly rely on doing everything in simulation and sim to real, but use simulation as a toolbox to get us to 80% and then close the final gap in the real world.
Okay, thanks for the answer. I'm happy to just pass down because I know we're gonna have the closed room session, right? So
Okay.
maybe just the next committee members.
Thanks, Karen.
Yeah, so when we have the closed session, it will be only with the faculty members. So if you have questions for them, you could ask them now. But if you have other concerns, we could discuss.
I see.
Them. Yeah.
Seems interesting. So okay, got it. That's okay. I think in the interest of time. And by the way, I have a hard stop before 11.
Before 11. Okay. Got it. Thank you.
Thank you, Aaron. Jason?
All right, we'll go to Jason next.
Yeah, thanks, Lance, for the great presentation. Very impressive body of work. So to start, maybe with a high-level question. A lot of your work is built on the idea of learning motor skills by imitating human behaviors, human motion data. And I think this makes sense for applications in, let's say, computer graphics and visual effects. But when it comes to robotics, why do we want to imitate human data? I mean, the bodies of robots are only superficially similar to the body of humans. The actuators are completely different. So why do we want those robots to move like humans? It seems like maybe we should try to get these robots to move in whatever way is most optimal for the particular bodies.
Great question. So the question is, why do we want to make our robot to move like humans when they potentially have more efficient ways of moving? So first of all, I think when we build humanoids, it is at a superficial level visually pleasing when the humanoids move like humans. I think that's the very first, the shallow stage. It looks cool, it looks good. The second is, I do believe if we let our humanoid move like human, we will unlock a lot more data for our policies. Because collecting mocap is relatively easy, and if we make our humanoid more like humans, move like humans, we would be able to imitate all of the motions that humans do. And collecting that kind of data, for example, mocap, or learning from human videos, because the embodiment gap from human to humanoid is close, and if we can let the humanoid learn human motion, we can unlock a lot more human data for training our agents. I think the data argument is somewhat driving the humanoid hype right now, because if we can use more human data for humanoids, we can really scale up. Because we're using humanoid, the biggest advantage of this embodiment is how close it is to human. And for the humanoid, you can see its own hand, and we can learn from egocentric videos for humans. And I think the data and learning from human experiences is what kind of the most motivation for trying to get our humanoids to move like human. And kind of going back to the OmniGrass work, where I showed the results, where if we don't have this type of prior and don't have this type of constraint, our humanoid can really search for very wild space, and maybe that's not as optimal. It could be a local optimal. And since we're building humanoid, I think we should let it to move like humans. Otherwise, why build a humanoid? Which is another can of worms why we're doing humanoids. But for a humanoid, I think we should let them move like humans.
Okay, makes sense. Well, I'm looking at some of the maybe recent results that's been released by various companies on, let's say, Unitary Boston Dynamics. There's some decision on robots being able to perform some really lifelike and agile behaviors. And it kind of seems like this, or at least from the results of these companies, you can build controls that can almost imitate anything that a human can do.
Mm-hmm.
So, if that's the case, isn't full body motor control pretty much solved at this point? Why don't we have humanoid robots running around?
So the question is humanoid locomotion solved?
Well, not locomotion, full body control.
Full body control. Oh, yeah, full body is full body control solved. I think we're getting close. We're making a lot of progress. But to put things in perspective, I still believe humanoid whole body control is at where graphics is in 2019 to 2020 or 2018. We are still at, Jason, your deep mimic stage, where we can imitate single motion really, really well. But all of the policies we have seen from Unitary Boston Dynamics, they're all one policy to imitate one single motion. They do not generalize. And I know every company is actually working on it to get it to generalize, and I believe we will see demos soon. But every one of these motions does require specific tuning, and maybe in some reward needs to be tuned for every single motion, and then some coefficient needs to be changed. The KP needs to be multiplied by 1.1, all these kind of magic tricks to make a cool demo. But we actually don't know how well they generalize, and how can we train one policy to do all kinds of different things we wanted it to do. So in our three axes, I would say they are still on kind of the whole body control and single task. They're not even on whole body control diverse tasks yet. We'll get there very quickly, but I think there is still work to be done. And then this is all still just whole body control without any interaction. The moment we involve, opening doors, moving heavy things, all these interaction, they will need whole body coordination, and those will need to be solved. And force interaction, that kind of things, and they will be very difficult to model in simulation and domain randomize. I think there is a still large amount of problems to be solved.
So they are blind.
Oh yeah, and they're blind. They don't even have dexterity. They're mostly just whole body control, and so they will be just around single task in the whole body control. Not even. It will be a decent amount of work to get to generalizable policies.
Okay. So maybe to follow up on the point about training specialized controllers for every single skill. A lot of your work has been trying to build these more general control models that, let's say, can imitate lots of different behaviors. And it seems like your approach is generally to try to use RL to train a general controller more or less from scratch to imitate lots of different behaviors. But I guess recently this kind of alternative paradigm using distillation where you train set of experts and you distill them into one general control general model. Can you discuss some of the trade-offs between these two approaches? So why not just train separate experts and distill everything into one big model? Why go through I guess in your case, why go through the whole hassle of trying to use RL to train one general controller?
Absolutely. So the question is, why don't we train multiple specialists and distill them into one generalist? I think that certainly is a great approach, and I think there is no fundamental conflict between what I am doing and distilling multiple experts, because the end goal is to train a generalist. Kind of intuitively, why I want to train generalists is I believe when you're trying to solve multiple tasks together, you find common strategies and skill reuse. For example, when grasping, what I have noticed is when you try to grasp one single object, and if you start to learn to grasping the simpler object, it becomes easier to grasp the larger, the harder object as well, because now you know how to approach, and you kind of know, okay, I need to grasp like this. So that there is a decent amount of skill transfers happening when you try to try this generalist policies. If you train individual islands of specialized policies, I believe there's going to be gaps in between when you are doing your distillation, and your policy won't be generalizing as well, because you learn one behavior, and they may have very different strategies for grasping the same object or similar objects, and you don't create synergies between these experts when you're doing distillation. And when you train generalists, you will be able to generalize a little bit better because you're trying to use similar strategies to solve diverse tasks. But that's just an intuition. I think both of these paradigms are very valid. In my collaborations, I try both. I think they will have to play out. But for my approach, I think training generalist, once you train the prior, it becomes much easier to solve other tasks, and which I think conceptually is a somewhat easier thing to implement. And yeah, it's easier, so I did it.
Sure, yeah, I think that's reasonable. Okay, so moving on to your work in manipulation on the grass. Right, so right now your approach is you train some low-level latent variable model, and then you have a high-level control on top, distributing RL to manipulate objects. But if you look at a lot of manipulation systems now, a lot of them rely on total operation, just simple supervised learning. So I'm wondering, why not just do that in only grass rather than training the model through RL?
Absolutely. So the question is, why don't we do teleoperation? So first answer would be, I think teleoperating humanoid in simulation is too expensive. That won't scale well. I think for real world use cases, teleoperation is an easier path than sim-to-real RL.
Why is teleoperation simulation harder than teleoperating a robot in real world?
Sorry, can you repeat that?
Oh, why is teleoperating a character in simulation more expensive than teleoperating?
Oh, I just feel like it is more. Since we're already in simulation and the collected data cannot be used in the real world, it's just we're going circular. If we want to do real world if we want to do teleoperation, I think it is more cost effective to try to get a policy to work in the real world. Yeah.
But let's say the goal was to get a policy to work in simulation, then it seems like the cost would be similar.
Yeah. So the second part is, I do believe for teleoperation, we usually get, since we don't have touch anymore for teleoperators, we usually, if you see all the demos, the humanoid is moving really, really slow. It's moving like very deliberately, grasp something and then put it down. For teleoperating in simulation, I have seen similar artifacts where the teleoperator needs to be really careful, move it and then grasp it, because you don't have this type of feedback anymore. And I feel like that's a pretty big issue in terms of the movement fluidity and agility, because now that your motion that you get from teleoperator is going to be really slow, doesn't look as human-like, because you're doing grandfather grasping. So with reinforcement learning, you can really get agile motions, move really quickly, and then grasp with a lot of confidence. And I do believe there are things that we cannot really teleoperate, like grasping heavier object, which OmniGrasp can actually generalize to. And I believe with reinforcement learning,
what if it's not possible to teleoperate grasping heavy object?
So it will be difficult, because if you consider we have a teleoperator system, the teleoperation system design will also needs to be force reactive. So we'll have to train, especially train policy for that. It needs to react, be very strong, and then react to your teleoperation behavior to support these larger objects, these more heavier objects, and your lower body needs to react to it, which I don't think, for example, PhD would be able to handle that type of reaction with heavier object. It would probably just crumble. So I think those parts needs to be ironed out if you're teleoperating in simulation. And I just don't feel like it is an easier problem if we're trying to teleoperate. If we already have the strong prior, learning a OmniGrasp policy is relatively simple once you design the reward.
I think those were mainly most of my questions. In the interest of time, I'll pass this on to the next.
Thanks, Jason.
All right. Thank you, Jason. We'll go to Shubham.
So actually, I'll first follow up on the teleoperation point or imitation learning point that Jason was making, that at least when people are doing manipulation, the typical approach really is imitation learning, and
yes,
because it's much easier than creating simulations of everything else, right? But what I really liked about your work is that there is this motion prior or sort of skill space or whatever you want to call it. And personally, I think it would be an interesting thing to explore that, okay, now, I mean, Tesla is training the humanoids to a large extent through imitation learning for manipulation, right? So, can your priors be helpful for someone who is doing imitation learning? Like, instead of doing imitation learning in raw space, maybe they'll do imitation learning in sort of your prior space, and that can speed up learning or increase robustness or something. So, is that something you've given some thought to, and would that be as easy as combining A plus B, that okay, now just I have this prior space, just this is like do imitation learning in this space?
Yeah. So thank you, Shubham, for the question. So the question is, can we kind of combine these two paradigms of imitation learning and the prior we have learned? I think absolutely we should. I think teleoperation, a lot of companies are doing teleoperation right now, and I from the field or in the air is teleoperation is not scaling that well. Some folks are hitting a wall. I do believe there is fundamental issues when you're teleoperating. For example, there's no force feedback, you're moving very slowly, it does not generalize well. I mean, we know behavioral cloning doesn't generalize that well unless you have infinite data, which is not possible for manipulation. So I do believe we should do add some RL on top, either through teleoperation or from scratch. That is debatable. But I have given some thought for a paradigm where you do RL assisted or prior assisted teleoperation, where, for example, the grasping motion is done with mostly RL, not from humans controlling every joint. What that can do is you can just kind of tell the policy, okay, do this, move your hand relatively here, and then grasp the object, kind of like a remote control, and let the low-level control prior to handle most of the things for you. And then we can keep updating this control prior. We give it an intent saying you should be grasping right now, and then collecting real-world rollouts. Like I've mentioned, once we have this control prior, we can start doing real-world rollouts. And real-world, that could be teleoperation. Like we can tell the humanoids what to do with this control prior and collect more samples and update our prior to really scale up this learning. So using the experience and the grounding we do in simulation to assist real-world data collection and build this kind of data pipeline to get more data from the real world, such that one day we can have more generalist policies.
But so in your answer, the role of RL is still critical to have this final controller, right?
I do believe that, yeah.
And I mean, whereas in what I was suggesting, the role of RL was just to have the prior space, and there's no RL since then. And I guess the reason I was advocating for that is if we think of open that Coke can, for instance, it would take someone a week in simulation to model the physics of that, and probably a sprite can will be different. And so on. So it's not very clear to me how manipulation you do RL assisted tuning for a lot of things, but
yeah, absolutely.
that was maybe more of a random comment as opposed to a well-found question. More concrete question on the manipulation aspect is you didn't go too much into details of the PHC-X, right? And I was just curious on what was the training data, what kind, like can it flip a coin, like what kind of motions can it imitate?
Yeah, so I actually do have one appendix on this, I think on the data. Fine. So basically, we have, don't have. We created more data for whole body human motion with dexterity. So we have, just hand motion, and we just paste that into the SMPRX humanoid and pair random hand movements with full body movement. And that's basically give us training data for dexterous humanoids, human motion, and then we just train it.
So even in this space, it hasn't really seen any forces or object interactions, right?
Yeah.
So for instance, if I were to now say, okay, use this space to dribble a basketball, where if you bounce something, it comes back, there's some force being applied on your hand.
Yeah.
Presumably in your simulation, you haven't seen that. So do you think the motion prior that you have learned, which is frozen for downstream applications, is it going to be expressive enough for these things, and if not, then how do we get around that?
I have used this prior to play Olympic sports.
Okay.
So it can throw basketball, it can hit tennis balls. So to a certain extent, yes, it has the expressiveness to handle forceful interactions, both on the feet and on the hand. And all the grasping is done with a prior that doesn't have interaction. So the motion prior is expressive. And I do believe there are actions like very fine-grained manipulation that will need to update the prior or learn the prior with interaction, which I have some collaboration on. We can scale up PHC policy if we have the data. We can always do imitation with objects and the current humanoid and train a better prior with forceful interactions. Motion imitation doesn't have to limit it to just the body. You can imitate full body motion with object as well. There's, I think, 3 or 4 papers on that. So we can get priors with forceful interactions.
Thanks.
Thanks, Ron.
Oh yeah, always a great speaker. Really enjoy it.
Thanks, man.
First, it's a technical question. A year ago, your thesis proposal asked, we create the pause latent space. You learn a prior. Is that because you're doing a unimodal stuff? And recently, there's a bunch of work doing flow-based or diffusion-based. Do you think you can actually, if you have like more powerful things that VAE, can you just, a better way to sample from the prior, better representation for the prior?
Yeah, absolutely.
What is your thought on that? Yeah.
Yeah. I am looking for better prior, better structure. I haven't found it yet. We have work using diffusion on the pre-train, and that operates on the pre-train latent space. It's a collaboration. But we haven't worked on that latent space itself yet. I do believe giving more better models like flow-based models, training a better control prior using diffusion is a very, very, very valid path. I haven't got the chance to try it. I do believe we should. I'm looking for many alternatives to pulse as latent space. I'm not 100% happy with it. I'm not super happy with it. It is a 2-stage, trains slowly, and we have to have the imitator. I want to do it in one go. Though diffusion probably won't be able to do that either. We'll have to do distillation. So yeah, I am searching for alternatives, and I think better models, better this type of generative models should be of great help here. But I haven't found the right recipe yet.
Got it. The second question, which is the last question for sake of time, is very high level. It's about like hierarchy and slow and fast things. It's also like follow up on Jason's question on why to imitate human. Actually, I'm a big believer we should imitate human, but why we have to do tracking? Why or like distillation tracking to either learn the prior or learn PhD? Do you think there should be some better representation than state-based tracking to learn either prior or like to learn skills? At least back to the hierarchy stuff. Like I'm a big believer. Like we actually do hierarchical thinking all the time. I don't think our muscle or we have a subcultural system, right? How do we actually materialize this kind of thing in humanoid learning? Do you think the next generation of PhD should be beyond tracking? What is a foundation behavior model? Do you think it's going to be tracking or something beyond tracking?
Yeah. So the question is tracking the task for training the behavior foundation model?
It's tracking the next token prediction for humanoid foundation model.
I do believe that. I think tracking is the simplest task you can tackle to get human-like motion prior. Tracking means we have great coverage. It means we are actually doing everything that our data wants the humanoid to do. So I think that's the benefit of tracking. And actually, a lot of the foundational behavior prior, like a mass mimic, multival, they all are using tracking as kind of a proxy task, either directly or like as a proxy task for judging the performance of your foundation prior. Because you don't have to train on tracking. I don't think you have to train on the tracking objective, but I think it is important to verify your tracking capability to make sure that your prior can actually do the things you want your humanoid to do. That is the benefit of tracking. It's an explicit test to say, can your humanoid do this motion? If you cannot, that means you don't have the control capability or control motor skills to perform these actions. So tracking is a good proxy task to make sure you can do certain things. Do you have to use tracking as the task to train control prior? Do we have to do distillation? No. I think I am looking for one-stage motion tracker, motion latent space, so we can do it in one go. Probably we'll have some tracking flavors in terms of the task and evaluation, but if we can form the pulse latent space in one sitting and train the policy, that would be great. I do not want to do distillation. I think there is some hyperbole going on with distillation. It's a complicated process.
Yeah, but if you in your z-axis, which is dexterity, for many human capability, we don't even have test specification, right?
Yeah.
Like the tracking to track something, right? For example, like the example Karen brought up, like lifting a box or this kind of thing. How do you even define the tracking trajectory? How do you define the test specifications? Yeah.
We have a lot of mocap.
Right.
We actually do have a lot of mocap, and then imitating from videos is also a viable approach, which is more science fiction-y. You look at a video and then you set up some environment, want to imitate that. There is a growing interest in the vision and graphics community to estimate 4D environment interaction with the object, and they are starting to use physics simulation for this purposes exactly. And I believe we'll get a decent amount of data with interaction and humanoid interaction, and with big small objects, many diverse interactions with object and humanoids.
Cool. Yeah, thanks. Yeah.
Thank you. All right, so I think we're a little tight on time, but we have a lot of people on Zoom and a lot of people in the room, so I think we could take maybe 2 questions from the room or from Zoom. So if you raise your hand on Zoom, David, or if there's a question, if you can let us know. Any questions from the room or Zoom?
I could ask a question. So a lot of your talk was motivated by like the humanoid form factor being good, right? So I guess what is a humanoid according to you, and what aspects of a humanoid similar to a human are important? Because clearly lots of these robots don't actually look like humans.
Really? You mean these?
Yeah, I guess the simulated ones.
Oh, the simulated ones. That's SMPL. That's perfectly human. But yeah, I think that's a great question. So, what defines as a humanoid? That's a little philosophical. 4 limbs, 2 hands, a head. And that's it. That gives you a humanoid. I think we should get closer. We are getting closer to the human form factor, and yeah, I think with these type of animation humanoid is actually closer to what these humanoids have, because these humanoids, the roll pitch are actually separate. That's not the anatomically, it doesn't look like an actual humanoid. But with these, they are a little bit more superhuman, but they have all of the freedom of the humanoid.
Thanks.
There's some questions on the Zoom though.
Okay.
What, you want to pick one first? David?
Okay. Pick one. This is around motion tracker.
Maybe we'll take that second one. Do you think the latent space learned by pulse is universal enough?
Oh, yeah. I think it is universal enough for a lot of tasks. When you use this type of motion prior, you will always have at the back of your mind, is this universal enough? So far, my answer is yes. It can solve a lot of the tasks. It's just a problem of design and reward. I think we will hit a wall though, and we should introduce more imitation, more data sets with humanoid object interaction in the loop, like something like what Mass Mimic is doing. Imitation is all you need. Just imitate every single data set you can have with your simulated humanoid, and you basically will have the motor skills required to do a lot of the tasks. And I do believe we should, at some point, try to update our learn prior. It should not be frozen all the time. I haven't found a good techniques. Maybe something like control maps, policy adaptation, something like that could work. But we should update our policy prior at some point, especially when we go into the real world, when there's a material gap. How do we update our control prior? How do we keep learning on the low level as well? I think that's going to be a very important question.
All right.
Tara has a hard question for you.
Not a hard question, but I think since we have a recording on Zoom and are here over camera, I'd love to ask a question that would be fun that we look back 10 years later. So do you think we can solve humanoid robots? If yes, when? If no, what would be the biggest challenge do you foresee for the next 10 years?
Oof. Are we going to solve humanoid robotics?
Yeah.
First, we have to define what is solve
Like you
humanoid
put a
robotics.
humanoid in your home. When do you think it's gonna happen?
I mean, it's happening right now.
I mean, not, yeah.
If we're talking about humanoid in-house, doing our chores, fold our laundry, I'm going to give the nondescript answer is 5 to 10 years, which means we translate to, I have no idea, it's a rough number, we're going to keep updating it. The biggest challenging problem, I think, it is multifaceted. It's going to be hardware, which is getting really close. AI, on the AI front, the brain front, we're very far, I believe. I think the biggest challenging we will face is going to be on the AI side. How do we train controllers? How do we actually do embodied AI? Embodied AI has been, be hyped everywhere, but how do you actually do things with control in the loop, with vision in the loop? One thing that I really like to think about is we don't even have artificial animal intelligence yet, and we want to do artificial human intelligence, and that's a little bit backwards in my mind. I think we should train just vision and action models and really get it to work. Grasping object, you don't need language, and that's why I designed the perception and interface. I really want to just train vision loop policies to learn to grasp in the real world, and once we have that, we can associate that with language. And I think that is going to be the major breakthrough we want to have, is associating this kind of high-level intent while obtaining the low-level controls using reinforcement learning or real-world data. And if we can connect them one day, we should be able to solve robotics.
All right, it is now recorded. So we're going to end the session here because we're running out of time, but thank you all for joining.
Thank you.